Welcome to AskPrep, your trusted companion for NEET and G preparation. Today we will study about a very important topic of physics, which is Simple Harmonic Motion, or SHM. This topic is crucial for NEET aspirants as it lays the foundation for understanding oscillatory motion, waves, and even quantum mechanics. Oscillations are everywhere around us, from the movement of a pendulum to the vibrations of a guitar string. When an object moves back and forth about a fixed position in a repetitive manner, it is said to be oscillating. But when this oscillatory motion follows a specific pattern where the restoring force is directly proportional to the displacement and acts towards the equilibrium position, it is termed simple harmonic motion. Here, F is the restoring force, K is the force constant, and X is the displacement from the mean position. The negative sign indicates that the force always acts in the direction opposite to displacement, ensuring the object returns to equilibrium. One of the simplest examples of SHM is a mass attached to a spring. If you pull the mass and release it, it moves back and forth in a regular manner, following SHM. Similarly, a simple pendulum also exhibits SHM for small angular displacements. The motion in SHM is periodic, meaning it repeats itself after a fixed time interval, called the time period, t. The frequency, f, is the number of oscillations per second and is measured in hertz. The relationship between time period and frequency is given by t is equal to 1/f. For a mass spring system, the time period of SHM is t is equal to 2π mk, where m is the mass of the oscillating body and k is the force constant. Another important parameter in SHM is angular frequency, omega, given by omega is equal to 2πf is equal to km. Angular frequency determines how fast an object oscillates. The displacement of a particle in SHM at any time t is given by the equation x is equal to Acos, ωt+, where a is the amplitude, maximum displacement, ωt+ is the phase of motion, and is the initial phase angle, which depends on the starting conditions. The velocity of the oscillating object is obtained by differentiating displacement with respect to time. V is equal to a omega sin, ωt+. Velocity is maximum at the equilibrium position and zero at the extreme positions. Acceleration in SHM is given by a is equal to omega superscript 2x. This equation shows that acceleration is also proportional to displacement but acts in the opposite direction. This confirms that the force in SHM always tries to restore the object to its mean position. Energy plays a crucial role in SHM. The total energy of an oscillating system remains constant but continuously converts between kinetic energy and potential energy. Kinetic energy, K, in SHM is given by K is equal to 1/2 m omega superscript 2, a superscript 2, x superscript 2. Potential energy, P, is given by P is equal to 1/2 m omega superscript 2, x superscript 2. The total energy of SHM is always conserved and is given by E is equal to 1/2 m omega superscript 2, a superscript 2. This means that as the object oscillates, its energy shifts between kinetic and potential forms, but their sum remains constant. At the mean position, kinetic energy is maximum and potential energy is zero, while at the extreme positions, kinetic energy is zero and potential energy is maximum. Now, let's talk about some real-life examples of SHM. One of the most common examples is a simple pendulum, which follows SHM when displaced by a small angle. Other examples include vibrations of a stretched string in musical instruments, the motion of a mass spring system, oscillations of atoms in a crystal lattice, the movement of car suspension systems. Apart from ideal SHM, in real-world scenarios, oscillations are often affected by resistive forces like friction and air resistance. This leads to damped oscillations, where the amplitude gradually decreases over time. If an external periodic force is applied, the system undergoes forced oscillations. When the frequency of the external force matches the system's natural frequency, a phenomenon called resonance occurs. This can lead to a dramatic increase in amplitude, which is observed in musical instruments, bridges, and even in electrical circuits. The time period, t, and frequency, f, are related to angular frequency by t is equal to 2 pi omega and f is equal to 1/t. The total energy in SHM remains conserved, with energy oscillating between kinetic and potential forms. The total mechanical energy of the system is given by E is equal to A12 Ka superscript 2. The motion in SHM can be analyzed through graphical representation. The displacement time graph follows a sinusoidal curve representing periodic oscillations. Similarly, velocity and acceleration vary sinusoidally, but with different phase relations. The velocity is maximum at the mean position and zero at the extreme points, while acceleration is maximum at the extremes and zero at the mean position. Damped and forced oscillations extend the concept of SHM. In real-life situations, friction or resistance reduces the amplitude of oscillations over time, leading to damped motion. However, when an external periodic force is applied, the system undergoes forced oscillations. If the frequency of the external force matches the natural frequency of the system, resonance occurs, leading to a significant increase in amplitude. This phenomenon has applications in bridges, musical instruments, and mechanical systems. Understanding SHM is essential for solving a wide range of physics problems in NEET. It is widely used in the study of waves, sound, and even quantum mechanics. The best way to master this concept is by solving numerical problems and understanding its practical applications. Thank you. If you found this explanation helpful, don't forget to subscribe to AskPrep for more in-depth NEET physics content. Keep practicing, and see you in the next session.